Hello, everyone. Hope everyone's awake after that delicious burger for lunch there. My name is Jimmy. Today we're going to be talking about avoiding microservice megadisasters. That was about the most dramatic title I could come up with to talk about microservices. So what we'll be talking about is a bit of an experience report of a company I work with and used to work at over the past 10 years or so. Now, in order to protect the innocent, I've changed a few names. This is a computer manufacturing company called Bell Computers, not to be confused with any other computer manufacturer. Now, this company had been around for quite a long time, over 30 years now. It was started in the 80s in a dorm room, that sort of thing. Now, for the first 10 years or so, the underlying systems that kind of ran orders and did manufacturing, everything, didn't really need to have much things going on. But eventually, sales grew, the company grew, and they needed one of these things. Does anyone know what this is? I've never actually seen one of these in person. I think they keep them in the basement somewhere. This is a mainframe. This is actually an HP tandem mainframe. It looks a lot fancier than I think that it actually is. I think it's just there's a hamster inside or something spinning on a wheel, something like that. Now, this mainframe did everything for the company. It did all these different areas and more. So any sale that you did went through this system. All the customer information was in here. All of the logistics information, all of the manufacturing data catalog, everything, absolutely everything was in this system. And of course, that worked great for a very long time. But because that system was COBOL, eventually it turned into one of these, a big pile of, I'll just call that mud, big pile of mud. This was the quintessential monolith because it did everything for the company, but it couldn't really do anything else. So around the turn of the millennium, turn of the century, they decided that, okay, it's time for us to come into the new millennium and actually have a website where people can go online and order computers. Now, for the longest time, this was a company that just did mail order and phone orders, and that was it. There was no online sales. So this is a big deal for this company to say, now we're going to move and actually sell computers online when our entire existing sales infrastructure is all 100% phone and mail order catalog based. So the architects got together, like they do, and drew some fancy pictures, and drew a design for their new Bell.com website. Now, each of the main parts of the system, because they were very different areas of the application, they actually had their own independently deployed servers, independently deployed websites. Everything was completely separate. In fact, if you go to some of these websites, and I often do, you can actually notice in the URL the subdomains changing as you're going from different areas of the application. And that's actually what they did here as well. So there's a separate catalog application, completely independently deployed, a separate account application that handled your personal information, things like that, separate orders and checkout application, and finally a completely separate search application as well. This is the picture they drew. The reality looked more like this, where everything talked to each other. This is around the time that they discovered that you can do link servers in SQL Server. So you can just have like joins between databases underneath the covers. It was a fantastic invention that resulted in an absolute mess. So even though they got away from their original monolith, it was still talking to the mainframe in the back end. And in fact, even today, if you go place an order on this website, it will still go through that back end mainframe. It's still there. So instead of that one big ball of mud, they just had about a half dozen different balls of mud because everything was talking to each other and everything was mixed up. Now, I wouldn't say that this was an unsuccessful deployment of their first attempt at service-oriented architecture because this website was 15 years in production. It launched around 2000, 2001. It was one of the first ASP.NET websites. It handled orders worldwide. They had different ordering systems in different areas or different regions. Billions of dollars in revenue flowed through this system with millions of orders a day, even handling the worst on Black Friday. But because of all these tangled dependencies behind the scenes, they had no way forward. So about 3 or 4 years ago, the architects got together again and said, you know what, we did such a great job architecting the last system, I'm sure our next attempt will be just as successful. And around that time, they started looking at how other large internet companies were building their systems. And they saw this picture of this company Netflix that was starting to build something else completely different in the service-oriented landscape. And then I saw this picture right here, which was a diagram of a request going into the system and the API calls that were happening behind the scenes to put together that request, and all these things happening in the time frame of milliseconds. So they saw this picture, had no experience really building anything like this, and said, right, let's do that because we're not going to do this tangled web of dependencies anymore. The team got together and wrote down a set of core principles of how they're going to build this new system. First of all was no data duplication whatsoever. They saw a major issue with the previous system of data being copied from database to database, and if anyone wanted to do something like change a customer's name or customer's address, they have to go to 13 different databases to do this. They saw this as a huge issue, so they said, no more of that, no more data duplication. It's going to reside in one place, and there'll be one true owner of that data. They wanted to have actual isolation and autonomy, not the pretend one they had before. And finally, because they heard it was a cool thing, they did web APIs for absolutely everything. If you needed to get information or needed to do anything, you had to use a web API to do so. And the final one is they wanted to get off that old mainframe that was built by someone else, in fact, and they called it Bell-on-Bell architecture, that they'd be able to run this on Bell servers and not on someone else's servers, which is kind of embarrassing when you have someone else's servers and you see the consultants walking in with their shirts on, and they give you these smug looks like, haha, you know, you make computers, but we make your computers, so we're better than you, that sort of thing. So they went away, designed this architecture, and went away setting about to actually build this. So they had a pre-production go-live, and what this pre-production go-live is, we don't want to actually release the application to everyone, so what we'll do is assign a set of servers to have a certain percentage of traffic to go to these. But first, let's actually run it on integration hardware just to see if it can all be fit together. Well, this required 18 months of effort to get to this point, involving hundreds of developers. And when they deployed it on the very best hardware that they could build. And because they build servers for their company, that's what they do, they can get it on the cheap. So even like the most crazy umpteen million core servers, they were able to put this on there. So they put all these on there. They went to a single catalog page to go just list a set of products, and nothing happened. Absolutely nothing happened. So they said, right, okay, that's awkward. It seemed to work on my machine. This is literally when we were doing a post-mortem, we were talking to developers. Yeah, how can you go 18 months and have nothing work? I said, it worked great on my machine. Like, oh, okay, here we go. So nothing happened. Absolutely nothing come up. So they said, okay, maybe let's put more hardware. Let's throw money at this problem. We build servers. Let's make the craziest rack backplane server we could possibly build. So this thing had it was a single rack that had a monster database server. It had gigabit black fiber connecting every single machine, and about the beefiest servers you could possibly imagine. And still nothing came up. So okay, we tried to solve this with hardware. Maybe it's a configuration issue. So they went to all the web services, all the little configuration parts, and said, let's up the timeouts to infinity. So the timeouts were originally set at 15 seconds, which should be enough for any web request, right? 15 seconds. So they upped all the timeouts to just datetime.max or timespan.max, and just said, we're going to wait forever until something comes up. So they did. They hit the website, hit the web page, just showing a list of products, and they waited. And they waited. And they waited. Fans started whirring. Heat started to dissipate from the servers. And eventually, 9.5 minutes later, the web page finally came up with a list of products. Now, you could step back a bit here and say, of course this is going to happen, because 18 months to ship anything is not micro at all. If you go away and spend hundreds of, let's see, it was about 150 million US dollars on developing this, hundreds of developers and a year and a half of effort, there's nothing micro about that architecture whatsoever. So after this, we did a post-mortem. This is when I came back after working there about 5 years earlier to help them figure out what went wrong with this architecture and how they can have some way forward. Then we're going to throw away everything, but we at least want to understand where exactly they went wrong. So we had our post-mortem, which is also known as a retrospective or a blame-storming session. Now, if anyone's tried to debug a monolith, it could be a very difficult thing to do. A monolith has lots of dependencies, lots of different things going on, and it could take forever to go trace through a request to see how this monolith is all put together. Well, it turns out debugging a monolith is about 1,000 times easier than debugging a distributed system full of API calls. So we want to understand how this one website, one web page went so wrong. When we went to the existing website, it didn't have great performance. The one that was on actually in production, the service-oriented monolith attempt. That one had, I think response times of about 3 to 4 seconds for some of the most complicated pages, which again isn't very good at all, but at least it came back in under a minute, let alone 10 minutes. So going back to trying to understand how this went so wrong, we decided to figure out exactly what was going on here. So we just start at the top. Let's just go to the very first thing that happens and then trace those requests throughout the entire process. It took us about 2 weeks later to build out the entire graph of everything that was happening because they completely misunderstood this picture. In this picture, we have one API request coming in that makes a series of server calls, but none of those other services make any other calls. And what's going on in this system that they had built was one API, I had the original request that would go to the web page. The web page would make a series of API calls. Those API calls would make another series of API calls, and then those API calls would make yet another series of API calls until we had hundreds of API calls crossing the network boundary just to serve one single request. So this picture, nothing ever crosses again. Nothing ever bounces off one of these and makes another connection. But this picture, with their architecture, was basically just a green circle because everything was calling everything, so it was just a complete washed-out picture of everything. So we had them do a little bit of math here with their website and their architecture they made. They had every API had to have some SLA that it was having to adhere to. And according to all the teams, they absolutely were adhering to this SLA. Okay, we'll get to that in a little bit here. But their SLA was every API call needed to return in 150 milliseconds with 3 nines of uptime, which they thought was not too bad. They have maybe about an hour or two of downtime a year. Nothing too crazy, but that's about the most they have. So I thought 3 nines, this should be pretty easy for us to do. Well, the problem was, when they built this API architecture, they built it in such a way that if any one API call failed, the entire application crashed. So if I have a couple hundred API calls and they just adhere to their most minimum latency of 150 milliseconds, then immediately we've got a 30-second latency in that original request. Even past that, this is assuming that they're all one after each other. We found in our dependency graph of all the different web services that we'd have API calls calling another API that then called the first API. So they were actually deadlocking themselves. They were having internal denial of service attacks, which is kind of an amazing thing to see. And if anyone here has taken any probability class or seen probability theory, if you have all these different calls that all have to work, that means that you multiply out your 99.9% uptime times 200 calls, and that effectively gives you 0% availability. Just using math and statistics, this system cannot work, and it didn't. So from the very beginning, this architecture was doomed. They set it on a path with over $100 million in budget, hundreds of developers to build something that was literally never going to work from the very beginning. Kind of a sad thing to see. So we asked the developers, okay, you went for 18 months developing this. You must have run the application once, right? Like, how did you get this far without ever seeing the performance that's truly awful? Well, it turns out that because all the teams were running at different rates and all the schedules are a little bit different, they never actually ran any of their local applications against any external services. And the few times they did do that, the other services were also running on that machine. So at no point when they were developing did they ever have to cross the network boundary in order to make one of these API calls. So of course, If you're running everything on your machine, that latency is not 150 milliseconds, it's more like 150 microseconds. And of course, the application performs absolutely great. The other thing we found was that they are all insistent that they were adhering to their SLA. So how is this possible? Because the app itself responds in minutes, but you're saying that you're adhering to your 150 milliseconds. They said, yeah, of course we are. Okay, how are we calculating that? Well, our work is this much. Yeah, we have to make this API call, but that's not us, that's them. So our SLA is really just the stuff we do. So no, wait a minute. Your SLA is the external agreement that you have to your service. And so what wound up happening is they didn't actually own their SLA because any one of those API calls was slow or broken would break their SLA. So instead of them owning their SLA, they were owned by their SLA. Yes, that's what they did. So I try to understand how they got themselves into this gnarly picture. And one of the architects sent me to a Microsoft article about how to build microservices. And it started out really great, and then went completely off the rails. So in this blog, they talk about how to build microservices. And it usually starts out with this picture that says, everything starts simple. We have an interior architecture where we have a web app talking to business logic, talking to a database. And if I want to scale up this picture, then I can put a load balancer in front of it and have multiple web apps talking to some sort of cache layer that has the business logic behind it, probably another cache layer as well, and then finally to the database. And this really resonated with the Bell developers because this picture was exactly the picture they had of their original website from the early 2000s. This is the exact architecture they had. Now, where things went off the rails was in how they architected the next piece. Their microservice architecture just broke up those in-tier pieces and broke up each individual tier or layer into a series of microservices. This is the exact picture that they had for their system. They said, okay, we have a set of front-end microservices that talk to a next set of back-end microservices that finally talk to the data microservices. And we have teams built around each of those pieces. See, though no team is larger than 2 pizzas or an elevator, so we're doing microservices. The problem is that microservices is not just taking your inter architecture and just shoving it on Docker or something like that. That's not what we're supposed to be doing here. Their traditional inter architecture, I've shown this diagram a million times, was something like this. This is what they started out with. But actually in the mid-2000s, they switched to DDD, so the architecture looked more like this, much better. And when they looked at different areas of responsibility of their application, when people were developing features in the system, they weren't developing features across individual tiers. Instead, they were developing in these big, thick vertical slices. And in fact, the original architecture of the application, each of these was its own independently deployed and developed application, all the way down to the database. So we went to the front-end system and said, you know, this at least works. Why does it work? Well, because catalog had its own database. Config had its own database. Cart and checkout also had its own database, and each of those databases were built and developed specifically for how those different parts of the application would be used. So for example, the search part of the Microsoft or the Bell website. Did anyone know that Microsoft actually had a document database in the mid-2000s? It was new to me too. They bought a company called Fast, which I guess is a great name to name your company. And it was a document database that was very similar to Elasticsearch. Unfortunately, Microsoft put this Fast Search under the SharePoint umbrella, so that's probably why you've never heard of it. It's SharePoint Fast. And no, SharePoint is slow, so of course you wouldn't buy a product called SharePoint Fast. So their front-end websites had a system in production that used 100 or 200 nodes, depending on the region, of this document database that was very highly indexed and performed absolutely great. But they replaced that with their one monolithic database behind the scenes because we can only have data in one place. In their search database they had online, product details were duplicated between the back-end catalog and the front-end search site, and because they don't want data duplication, they needed to have the search site actually go to the catalog service to do any search. Now, the catalog team knows how to make relational databases because these products have different relations to each other and SKUs have different relations. They don't know the first thing about search, but we're forcing that upon them because no data duplication. So I had them take a step back and say, look, your concept of a service has gone completely off the rails. And I can kind of see why, because if you try to go just Google service-oriented architecture or microservice architecture, there's just a sea of information, usually pushed by specific vendors. So if we want to go back to sort of the original definitions and try to see what those meant, I try to go to 3 primary sources. One of the sort of original SOA folks, one of the domain-driven design folks, and another is the microservice people. So I want to compare and contrast what are the different definitions of a service. What does that mean to each of them? From the service-oriented architecture group, a service is software that is owned and built and run by an organization. Now the key word there is going to be owned, ownership here. Responsible for holding and processing and distributing kinds of information within the scope of that system. Can be built, deployed, and run independently, meeting defined operational objectives, so it meets an SLA. Communicates with consumers and other services, presenting information using conventions or contract assurances. And finally, protects itself against unwanted access and its information against loss. And finally, handles failure conditions so that failures cannot lead to information corruption. It's a very long-winded explanation for basically services must be autonomous. Now, microservice has a much shorter definition. I guess it's because it's micro. A microservice is small and focused on doing one thing well. Now, what is the one thing? That's up to the reader to decide. And it's autonomous. And that's basically it. It's autonomous and it does one thing well. And finally, and they use the town planning metaphor to describe how these services are built. So you have some sort of metaphor in your head when you're designing this sort of system. And finally, from the domain-driven design crowd, we have the concept of a bounded context. The bounded context delineates the applicability of a particular model. Now, this is very, very critical for the Bell folks to understand, because their concept was if we can only capture the data and store it at one particular place, they don't have to have 18 different definitions of a customer. Now, the problem is, if you actually went to the business and talked to them, they never actually agreed what a customer was in the first place. So how can we build a system that doesn't actually conform to what the business is actually doing in the first place? So a sales team has a particular vision of a customer. A customer to them is someone that might in some point buy something, or maybe in the past bought something. When we go to the order system, a customer is strictly someone that has bought something. It has no concept of some other set of people that could buy something in the future. So immediately, these two groups didn't have a similar concept of a customer to begin with, but we were forcing them down this path by having all the customer data in one giant table that had, 300 columns. Lots of fun stuff there. Inside this bounded context, we have a logically unified model. We encapsulate internal operations and define explicit contracts for external communication. So it's a very, very similar definition to what we saw from the SOA crowd. And the metaphor they like to use is in terms of cells. How cells are autonomous, they can do pretty much everything they need to, and there's an external API to those cells using proteins and things like that to have other cells communicate to them. So when we came in, we finally got them sort of on track of understanding that their service-oriented architecture vision was completely wrong, and we now want to try to go to fix it. So the rest of this will be about how we fixed one part of their application. We couldn't fix all of it because it was just too big for our small company to deal with, but we at least wanted to provide an example of how to build it through one small part. In that case, we were looking at the search part of the website. Now, the first thing we had to convince them was this concept of no data duplication was an utter farce. And one of the really great papers I read that really helped seal and put this concretely for them was a paper called Immutability Changes Everything from Pat Helland. Now, I don't do appeal to authority a lot, actually I do it all the time, but Pat Helland was one of the designers of the original SQL Server database. He designed the part of the system that did distributed transactions, two-phase commits, and he also designed that weird queuing system that exists inside SQL Server. Does anyone ever use that too? I didn't know it existed, but you can actually have queues inside SQL Server. He built those two things. And he completely changed his mind about that sort of architecture and said, you know what, that stuff is rubbish. It doesn't actually scale. Instead, we have to think of things in much different terms. And his idea behind immutability is that if data doesn't change, then I can duplicate it as much as I want. If I don't allow people to change that data, I could hand it out like candy. And in fact, when we showed their architecture of Bell back in the mid-'80s when they're doing strictly mail order catalogs, this duplicated data was everywhere. They sent out these catalogs to 1 million people, and that data was literally physically duplicated on each of those pages. So I asked them, okay, you've already gone through this architecture of duplicating data, printing these catalogs out and sending them out to millions of people. What do you do if the price changes and you have to update something? Oh, well, we wait for the next quarterly catalog and we send an update. Oh, so you have a trade-off then. You have a trade-off for immediate results versus scalability. There's already a trade-off there. So I then asked them, so when you print these catalogs, can customers write in their own prices? Can they just cross out, oh, I don't like that for $200. How about $50? How about $5? Do you allow them to do that? It's like, no. Oh, so even though you're handing out this data and it's duplicated, you're not allowing them to change it. And if they do change it, you don't actually honor their changes. So they actually had the solution to them right in front of their face, and all other modern internet applications had also figured this out and built the exact same architecture that existed for hundreds of years, just writ large and quick on the web. So we looked back and looked, well, how does their existing search website work? In this microservice architecture they had before, when I make one request to the search website, it didn't actually hold any data itself. It was going and calling. In this case, I just have 4 up here, but there's actually about a dozen that would call. And it would make all these different calls to pull together all this information. And the way to get to 200 API calls for one single page is you make one API call for the catalog to say, can you give me all the products in this specific catalog? And they'll say, sure, here's 1,000. Because they don't know paging, because catalog doesn't need to know about paging. It's just, here's all the products I have. Okay, let me get all the catalog data back. Oh, I need pricing, but pricing is in a different service. So for each one of those catalog items that I show on the page, let me go ahead and call the pricing service to get the individual price based on your country, your region, also which part of the website that you click through as well. Now that I have all those prices back, oh, they're not showing the right localized data for this information. So let me call the localization service for every single snippet of information I would show on the screen. So that was about 100 calls just with that through the localization service. And finally, for content, for images and things like that, I need to call the content service. Well, this is how you get to 200 API calls in one page. And I didn't even show the times when these services were calling other services. That sort of crazy was going on as well. Because catalog and pricing needed to serve everything in the organization, it became a superset of all the data that anyone could possibly need in a single API call. So this REST API that they were calling was basically multiplied times 1,000 to show the search results of any one page. Now, we went back and looked at the different areas of responsibility in the original monolith, and it turned out that in addition to catalog, config, cart checkout, they already had an existing search service that worked in production. So we said, why don't we do this? Okay, all that code is just shoved inside this monolithic front-end application. Why don't we just slice out all those pages and all that code and put it into a new application, and this will be our new going forward service for search. But we need to make sure we extend that bar all the way down to the database, just like you do today. So I'm not even arguing for a new architecture. I'm just saying, why don't we just make the boundaries more explicit, but otherwise we can do the exact same thing you're doing today in production that actually works. So we went back to looking at the data duplication problem. And looking at search needed to actually own what that data looked like. Now, in the backend system, they had normalized data sets, things like that, but on the front-end search side, the users don't see that. They just see a single page with product data. And so all of that product data needs to be in some format that is most optimized for the search service. So search really needs to own what that shape of the data looks like. They also need to own the SLA response. And we told them, you can't just calculate your SLA based on what you do. You have to calculate what you do plus anything else you call. So you need to own that SLA. And they're like, ooh, gosh, well, those teams are full of idiots. Those teams are full of idiots. Those teams are full of idiots. We can't trust any of those jerks, so we don't want to call any of them. If we're going to return back, if we're going to guarantee a response time of 150 milliseconds, then the only way we can guarantee that is if we own the entire response chain and don't talk to anyone else. It's like, great, you're on the right path now. This is another funny thing. They need to own the relevance of items. When you went to the deployed websites, after they did all their hardware optimizations. And if I searched for Windows 10 in the search bar, what came up were t-shirts and mugs and little koozies and things like that. That's what came up with a computer website, was a bunch of other junk that had nothing to do with computers. I said, why is this doing this? I said, oh, because we're calling to the product service. And they don't really have any sorting of their data, so it just comes, that's just what comes back to us. But we can't get them to change because they don't understand search. They don't understand relevance. So, okay, well, in order for you to actually own this SLA and own the response, then you really need to own the behavior of that search. But you don't get to own any of the actual data. Any data you get in, you can't manipulate it. You'd have to take it as is because that's what the backend systems own. So the next thing we did was set about trying to break all the different places they were calling out to those external services and see if you in this request are not going to call to any external service, then how are we going to make sure that that doesn't happen? Well, only by going through each of those different connection points and saying, how are we going to sever these connections? So the first one we looked at was catalog. Catalog was interesting because it had super complex configuration. So when you go to one of these computer websites, unless you go to Apple, there's no real complex configuration there. You basically get colors, I guess. But if you go to like a regular developer laptop, manufacturing websites, they've got 100 different drop-downs that you pick and select some, and it changes the price of the information. If you choose this hard drive, that invalidates this RAM, or if you choose that kind of processor, it invalidates this kind of RAM. And so you have this really set of complex configuration. Well, you only get that complex configuration when you actually go to click a button that says configure. And if you go to the URL, you actually notice you get transported to a new website that says config.bell.com. But on the search results, we don't have that complexity in the configuration. What they have are things called standard configs. These standard configs are what they used to just mail out to people in the mail order catalogs. You've probably seen these advertisements that are like, here's this computer that has this configuration for 20,000 kroner or whatever it might be. And so that sort of standard configuration is actually well known up front that says this is what you start with, and then you can configure from there. So if I know this, I also know there's a known quantity of these. And we went back and looked, there are about 1,000 standard configurations. Now previously when they were trying to sort of suck in all the data themselves, they went through each configuration and went through every combination and permutation. So there were billions and billions of different prices that were being stored in the price catalog because we had to go through every single combination there. But if we just focused on the few standard ones we had, then there was only 1,000 of these. And we also learned that this information doesn't change often. We also learned, talking to the catalog people, that if information changes, the people in the back end actually don't expect it to show up immediately. They're already sort of trained to have a nightly batch process. So he said, okay, then what we'll do is catalog, you can keep your horrible soap service, but what we're going to do is have a little batch job that runs once a night, calls your catalog API, and gets the standard prices for each of the standard configurations once a day. Now, we didn't tell them this. We just did it because we didn't really like that team, and they didn't really play well with us. So we said, fine, we'll still use your dumb API. We're just not going to use it the way you want us to. We're going to just call it once a day. So with that, the pricing information, the catalog information was taken out and then stored in our document database. Now, pricing was its own separate monster. Pricing depended highly on the configuration. And in order to get a price, you had to send the entire configuration to the pricing service. It would do some sort of crazy calculations and then return you back the actual price. The pricing itself, of course, depends on the configuration. If you have different RAM or different hard drives, you'll have a different price. It also depends on the region. So if you live in different places, you get different prices. If you live in Australia, just double the price. That's what you get. It also depended on the catalog. So if you come in through the website saying I'm a home business user, or if you go in saying I'm an enterprise user for the same exact computer, the same configuration, you get a different price. So just FYI, click around the websites a bit to see if you get different prices, because sometimes you do get better prices. But the funny thing was, the price was actually served with a catalog. When we went back and looked at the catalog API result, we're like, wait a second, there's a price there. Why don't we just use that price? Why do we have to go make a separate call? They've already got this data. We asked the catalog team, even though we weren't on good terms, hey, what's going on with that price there? They said, oh yeah, one of the back-end sales systems, they were really complaining they didn't get their prices. And that's one thing you'll know in these sort of organizations. It really is whatever the sales team wants is what the IT people do, because they're the ones that really drive the business there. So we just severed the connection and never called the pricing service ever again. And the pricing people won because suddenly they had great load times. Like, oh, wow, our service can actually return because we're not getting called thousands of times a day. I wonder what happened. Oh, well, and they kind of moved on. The next part was localization. This was a piece that rarely changed. In fact, most of the localization data was done even like years earlier, put into some localization database, and then served out. Localization drives many, many internal clients. So in addition to the front-end website, there's a lot of tools on the sales side and everywhere else in the company because we'd have sales reps worldwide, and so we'd have all these different localized information on all those different places. So we asked them, okay, this localization stuff is complex. How are you doing this today? Oh, well, 15 years ago, when the localization service realized that they couldn't build this architecture with a synchronous API, they just caved and put a flat file on a share drive that said, right, stop messing with us, guys. Just here's the localization data. Do whatever you want with it. So we just chose the existing integration method. Once a day, we went to that flat file format, pulled in, and just did a bulk insert of all that data, of all the localization information, and called it a day. Now, we didn't know what changed with that localization data. There was no sort of indication that these were added, these were removed, these were modified. So we just said, okay, fine, we'll just wipe all of our localization data, takes about 2 seconds, and then shove all the new stuff in there, and then we'll call it a day. Consuming files once a day, using the existing integration method that had been there for years, and of course, everyone is happier. Now, the final one was one of the more fun ones, which was content. Content was stuff that did change frequently. And in fact, they really want to have these changes go out very, very frequently. The existing front-end system, the way it worked, was there was a back-end database for the management of the data, and then twice a day, every 12 hours, they would just swap the production and the production and the back-end databases, just using DNS, and say, right, now the production data is the back-end data, and the back-end data is the production data, and then they go on from there. So it was really just a bulk move of all that data information to the front end. Now, what's interesting, in the new architecture on the microservice side, we went and talked to the business and said, hey, guys, do you know that whenever you change content, because we can't duplicate data, it's showing up immediately on the front-end website? And they flipped their minds. At no point did they ever instruct the developers that they wanted this information live. They had actually baked into their approval process of content the knowledge that it gets swapped out twice a day. So when they wouldn't change content, they would actually get manager approval to say, hey, does this look right? Because once you put it on the front-end website and something's wrong, then you can wind up selling something for much cheaper, or it looks wrong, or whatever it might be. So they had this twice-a-day system that they went actually backwards from and said all this data is always live. So we said, right, we want to go back to that system, but we have our own document database, so we just can't take your existing backend system. But the problem is the content team, they weren't willing to go back to their old system. They'd already trashed it. They had a new database, new system, new everything, so they really couldn't go back to where they were before. So with those frequent changes that we want to be able to react to quickly, the way we did this, without really annoying too many of them, is put triggers inside the database. So then when they change some row, it would use messaging to generate a message that our search service would then subscribe to and then be able to put those changes in on our side. To do the 12 hours changes, we just put a simple buffer in front of handling those messages that only 12 hours we would wake up and then actually consume those messages and put them to our system. Now, it looked ugly because it was triggers, but it worked, and we didn't have to touch any of the the application code of the content team. We just went back into their database, bought the DBA a steak dinner, and he put in these triggers for us. So the final picture looked like this. Instead of my search service having to call out to all those other services, instead there were back-end processes where all these services were feeding their data into a denormalizer, into my document database that the front-end system can actually use to perform actual searches. As part of the denormalization process, this is where we do our search ranking. So we'd use things like clickstream data from people going through the website to boost results of some things over the others. But we owned all that information in that SLA so that when you hit the search website, it only went to that document database and nothing else. It was fed by a lot of other services, but in order to make that outside external request, I only ever went to that one spot. So with this example in play, they had a nice, great example architecture of how to take that and go to all their other services, and they had a wildly successful microservice deployment, right? No, unfortunately, search was the only one they actually did this with. It turns out that their team structure, they did move towards this, where each team more or less owned each of these different pieces. They would own the app, the database, and everything else. But unfortunately, one thing I learned from this company a long time ago was that architecture does not solve organizational problems. If your organization is crap, then there's nothing your architecture can do to fix those. And so the key problem that this organization had was each of these teams not only had their kind of mentoring and one-on-one structure for the developers, they also had their boss as part of this team. And the only way you could advance in this company was to build a bigger and bigger team. So they couldn't actually do microservices because people that were earning more money were incentivized to not break things up. So while the apps themselves weren't those piles of poo, the people leading the teams were, and so they didn't actually get to that final end result. So they almost got there. We got one nice service in there. None of the other ones were able to get there, but I can at least say we had that one good success there. So that was avoiding microservice megadisasters. Thank you very much, and have a great rest of your conference.